Spectral lines serve as cosmic fingerprints that enable astronomers to decipher the chemical and physical nature of celestial objects across vast distances. These distinctive features in the electromagnetic spectrum have revolutionized our understanding of the universe by providing critical information that would otherwise remain inaccessible through direct observation alone. By analyzing the unique patterns of absorption and emission lines produced by different elements and compounds, scientists can determine the composition, temperature, density, and motion of stars, galaxies, and interstellar gas clouds without the need for physical samples. This remarkable capability forms the foundation of modern astronomical spectroscopy, which has evolved from simple prism-based observations in the 19th century to sophisticated multi-wavelength analysis techniques employed by today's most advanced observatories. The insights gained through spectral line analysis have led to numerous groundbreaking discoveries, from the identification of previously unknown elements to the detection of exoplanets orbiting distant stars. Spectral lines represent specific wavelengths in an electromagnetic spectrum that appear either brighter or darker than the surrounding continuous spectrum. These distinctive features emerge from the fundamental interaction between photons and quantum systems, primarily atoms and molecules, when energy transitions occur between distinct quantum states. When atoms absorb photons with precisely the right energy to elevate electrons to higher energy levels, they create absorption lines in the spectrum. Conversely, when excited electrons return to lower energy states, they emit photons of specific wavelengths, producing emission lines. The energy difference between quantum states is unique to each element and molecule, creating a distinctive pattern of lines that serves as an unmistakable identifier. This phenomenon is explained by quantum mechanics, which describes how electrons in atoms can only exist in discrete energy levels rather than at any arbitrary energy. The resulting spectral patterns are so distinctive that they allow astronomers to determine with remarkable precision which elements are present in objects that may be billions of light years away from Earth. Each element and molecule produces a characteristic set of spectral lines at specific wavelengths when observed under controlled conditions, creating what amounts to a unique optical signature. Hydrogen, the most abundant element in the universe, generates a well-known pattern of spectral lines, including the Balmer series visible in the optical spectrum and the Lyman series in the ultraviolet range. Similarly, other elements like helium, calcium, and sodium each generate their own distinctive spectral fingerprints that can be identified in astronomical observations. These spectral features remain consistent regardless of where the element is found in the universe, provided it exists under similar physical conditions. The consistency of these patterns means that spectral lines serve as reliable cosmic barcodes, allowing astronomers to inventory the chemical constituents of celestial objects despite their immense distances from Earth. This fundamental property makes spectroscopy one of the most powerful tools in the astronomical toolkit, providing information that would be impossible to obtain through other observational methods. The quantum mechanical basis of spectral lines lies in the discrete energy levels that electrons can occupy within atoms and molecules. According to quantum theory, electrons cannot possess arbitrary energies, but are restricted to specific energy states determined by quantum numbers. When an atom absorbs a photon with energy precisely matching the difference between two energy levels, an electron jumps to a higher energy state, creating an absorption line in the spectrum. This excited state is unstable, and the electron eventually returns to a lower energy level, releasing a photon of specific energy in the process. If the atom is part of a hot gas emitting radiation, this creates an emission line at the corresponding wavelength. The precise energy differences between these quantum states are unique to each element and isotope, which explains why spectral patterns can serve as reliable identifiers for specific atoms and molecules. The quantum mechanical nature of these interactions ensures that the wavelengths of spectral lines are highly consistent and predictable under controlled conditions. The photon energy involved in these transitions follows the relationship E/hn, where E is energy, h is Planck's constant, and n is the frequency of the photon. This relationship directly connects the energy difference between quantum states to the wavelength of light absorbed or emitted, establishing the basis for spectroscopic analysis. In more complex atomic systems with multiple electrons, the possible energy transitions multiply, creating richer spectral patterns that can reveal not only the identity of the element, but also its ionization state. For instance, neutral hydrogen produces a different spectral pattern than ionized hydrogen, allowing astronomers to determine not just the presence of hydrogen, but also the physical conditions that would cause it to be ionized. This quantum mechanical framework provides the theoretical foundation that makes spectral analysis such a powerful diagnostic tool in astronomy. Astronomers observe two primary types of spectral lines: absorption lines and emission lines. Absorption lines appear as dark features against a brighter continuous background spectrum and occur when light from a hot source passes through a cooler gas. As this light traverses the gas, atoms absorb photons at specific wavelengths corresponding to their energy level transitions, effectively removing those wavelengths from the original spectrum. The cooler gas then re-emits the absorbed energy in random directions, resulting in a reduction of light intensity at those specific wavelengths when observed from a particular direction. Stellar atmospheres frequently produce absorption spectra, where the hot interior of a star generates a continuous spectrum that passes through the cooler outer layers, creating a pattern of dark absorption lines superimposed on a rainbow-like background. These absorption features in stellar spectra provide crucial information about the composition and conditions in stellar atmospheres, allowing astronomers to classify stars and understand their physical properties. Emission lines, conversely, appear as bright features against a darker background and are produced when atoms in a hot, tenuous gas are excited and subsequently release energy in the form of photons at specific wavelengths. Nebulae, which are clouds of gas and dust in interstellar space, often display prominent emission spectra when they are energized by nearby hot stars. The ultraviolet radiation from these stars excites the gas atoms, which then emit visible light at characteristic wavelengths as electrons return to lower energy states. The resulting emission lines create the distinctive colored appearance of many nebulae, with hydrogen often producing the red hues and oxygen contributing the green and blue components. Both emission and absorption spectra reveal valuable information about astronomical objects, but the type of spectrum observed depends critically on the geometry of the source, the temperature differentials involved, and the density of the material producing the spectral features. The relative strength of these lines provides additional information about the abundance of elements and the physical conditions within the observed region. The classification and designation of spectral lines follow established conventions that help astronomers communicate their observations precisely. In the visible part of the spectrum, many prominent lines have been assigned Fraunhofer designations, named after Joseph von Fraunhofer, who first systematically cataloged solar absorption lines in the early 19th century. For example, the K line at 393.366 nanometers is produced by singly ionized calcium, Ta+, while the prominent sodium D lines appear at 589.0 and 589.6 nanometers. Beyond these historical designations, spectral lines are also classified according to their ionization state, with Roman numerals indicating the level of ionization. Neutral atoms are designated with the Roman numeral I, singly ionized atoms with the psi, and so forth, creating a system where, for instance, Fe III refers to iron that has lost 2 electrons, Fa2+. This nomenclature system allows astronomers to specify not only which element they have detected, but also its ionization state, which provides valuable information about the temperature and energy conditions present in the observed object. Spectral lines are further grouped into series based on the quantum transitions that produce them. The Balmer series in hydrogen, for instance, results from electron transitions that end at the second energy level and produces several prominent lines in the visible spectrum. Other important series include the Lyman series, transitions to the ground state, in the ultraviolet region, and the Paschen series, transitions to the third level, in the infrared. The patterns formed by these series were crucial to the development of quantum mechanics and atomic theory in the early 20th century. These classification systems enable astronomers to efficiently communicate about specific spectral features while also conveying information about the underlying atomic processes. The organized cataloging of spectral lines has built a vast reference library that astronomers can use to identify elements in celestial objects by comparing observed spectra with laboratory measurements of known elements under controlled conditions. Spectral line analysis serves as a cornerstone of modern astronomical research, providing insights into virtually every aspect of celestial objects. One of the most fundamental applications is determining the chemical composition of stars, planets, nebulae, and galaxies. By matching observed spectral lines with known laboratory patterns, astronomers can identify which elements are present and in what relative abundances. This capability has revealed that hydrogen and helium dominate the composition of stars, while also detecting trace elements that provide clues about stellar evolution and nucleosynthesis processes. Beyond simple identification, the relative strengths of spectral lines indicate the abundance ratios of different elements, helping astronomers track how the chemical makeup of the universe has evolved over cosmic time, as successive generations of stars have synthesized heavier elements from lighter ones. This chemical analysis extends to interstellar clouds, planetary atmospheres, and even the most distant galaxies, providing a comprehensive view of cosmic chemistry across space and time. Spectral lines also reveal crucial information about the physical conditions within astronomical objects. The broadening, splitting, and shifting of spectral lines provide measurements of temperature, pressure, density, and magnetic field strength. Thermal Doppler broadening, for instance, occurs because atoms in a hot gas move at different velocities, causing slight shifts in the wavelengths of emitted or absorbed photons. The width of the resulting spectral line directly correlates with the gas temperature, providing a reliable temperature measurement technique. Similarly, pressure broadening occurs when atoms collide, temporarily distorting their energy levels and broadening the spectral lines. The degree of this broadening indicates the density and pressure of the gas. Magnetic fields cause spectral lines to split into multiple components through the Zeeman effect, with the separation between these components revealing the field strength. These physical parameters, derived from subtle features in spectral lines, provide astronomers with detailed information about conditions inside stars, interstellar clouds, and other cosmic environments that would otherwise remain inaccessible. Perhaps one of the most powerful applications of spectral line analysis is the measurement of motion through the Doppler effect. When a light source moves relative to an observer, its spectral lines shift toward longer wavelengths. Redshift, if it's moving away or toward shorter wavelengths. Blue shift, if it's approaching. By measuring these shifts in spectral lines whose rest wavelengths are precisely known, astronomers can calculate the radial velocity of objects with remarkable precision. This technique has numerous applications, from detecting the wobble of stars caused by orbiting planets, leading to the discovery of numerous exoplanets, to measuring the rotation of galaxies, revealing the presence of dark matter. The Doppler method has proven particularly valuable for measuring the expansion of the universe. By observing that distant galaxies show redshifts proportional to their distance, astronomers confirmed that the universe is expanding and have measured its acceleration, leading to the discovery of dark energy. These velocity measurements, derived from spectral line shifts, have profoundly shaped our understanding of cosmic structure and evolution. The spectroscopic analysis of binary star systems further demonstrates the power of spectral line observations. When two stars orbit each other, their spectral lines periodically shift back and forth as one star approaches Earth while the other recedes, then vice versa as their orbital motion continues. By tracking these spectral shifts over time, astronomers can determine the stars' orbital periods, the shapes of their orbits, and even their masses. Similar techniques apply to discovering and characterizing exoplanets, where the much smaller spectral shifts caused by a planet's gravitational tug on its host star can reveal the planet's mass and orbital parameters. In galaxy clusters, spectroscopic measurements of member galaxies' velocities provide estimates of the cluster's total mass, including its dark matter content. These diverse applications demonstrate how spectral line analysis has evolved into a versatile toolkit for astronomers studying cosmic objects at all scales, from planets to superclusters of galaxies. The history of spectral line analysis is marked by numerous groundbreaking discoveries that have fundamentally altered our understanding of the cosmos. One of the most celebrated is the discovery of helium, which was first detected through its spectral lines in the solar spectrum during an 1868 solar eclipse, before it was ever found on Earth. This marked the first time an element was discovered in space before being identified on our home planet. Similarly, the elements cesium and thallium were discovered through their distinctive spectral signatures. These discoveries demonstrated the power of spectroscopy to reveal the existence of previously unknown elements. The development of spectral analysis techniques by pioneers like Joseph von Fraunhofer, who identified hundreds of dark lines in the solar spectrum, and Gustav Kirchhoff and Robert Bunsen, who established the connection between spectral lines and chemical elements, laid the foundation for modern astrophysical research. Their work transformed astronomy from a primarily descriptive science focused on positions and motions to one that could determine the physical and chemical nature of celestial objects. The application of spectroscopy to stellar classification led to the Harvard Spectral Classification System, which organizes stars into spectral types based on their spectral features. This classification system, refined into the familiar OBAFGKM sequence, revealed that stellar spectral differences primarily reflect temperature variations rather than compositional differences. Later, the Hertzsprung-Russell diagram, which plots stellar luminosity against spectral type, became a powerful tool for understanding stellar evolution. In the early 20th century, the analysis of galactic spectra by Vesto Slipher and later Edwin Hubble revealed the redshift distance relationship, providing the first evidence for the expanding universe and laying the groundwork for the Big Bang theory. Throughout the 20th century and into the 21st, spectroscopic techniques have continued to evolve, expanding beyond the visible spectrum to encompass the entire electromagnetic range from radio waves to gamma rays. This technological progress has consistently opened new windows into the universe, demonstrating the enduring significance of spectral line analysis in astronomical discovery. Spectral lines stand as one of astronomy's most powerful investigative tools, providing a wealth of information about celestial objects that would otherwise remain hidden from view. Through the analysis of these distinctive features in the electromagnetic spectrum, astronomers can determine the chemical composition, physical conditions, motion, and even the evolutionary history of stars, galaxies, and other cosmic entities. The quantum mechanical nature of spectral lines ensures that they serve as reliable cosmic fingerprints, allowing scientists to identify specific elements and molecules across vast interstellar and intergalactic distances. From their role in discovering new elements to revealing the expansion of the universe, spectral lines have repeatedly transformed our understanding of the cosmos and continue to drive astronomical research forward. As spectroscopic technology advances, enabling observations across the electromagnetic spectrum with ever-increasing precision and sensitivity, the analysis of spectral lines will undoubtedly remain central to astronomical discovery for generations to come, continuing to unveil the secrets of our vast and dynamic universe.